we have studied about the principal quantum number n, which describes the orbit or shell. So, orbit is the size and energy of an orbit is described by the principal quantum number, and it also provides the solution of many basic features like the radius, velocity, etc. And it was proposed by Niels Bohr. Now, we will move to the second quantum number, that is the azimuthal quantum number. So, the second quantum number is azimuthal quantum number, or it is also known as angular quantum number, and it was or also called subsidiary quantum number. This was proposed by Arnold Sommerfeld. Okay, and this is denoted by L. So, what does the azimuthal quantum number describes? It describes the shape of electron cloud and number of subshells in a shell or in an orbit. Okay. So, n was the orbit or shell and L is the subshell. Okay, and L describes the shape of the electron cloud. Electron cloud has various shapes like spherical, dumbbell shaped. So, these are all given by the azimuthal quantum number L. Now, there can be various subshells in an orbit. So, the number of subshells in an orbit is equal to n. That is, the number of subshells is equal to the principal quantum number n. Now listen very carefully. A subshell is denoted by L, but the total number of subshells that is present within an orbit is equal to the principal quantum number n. That is, if n is equal to 1, then it will have, that is, the first orbit will have, first orbit has one subshell. Okay. If n equal to 2, then second orbit has 2 subshells. Okay. Whatever will be the principal quantum number, that many subshells will be present within that orbit. Like for n equal to 3, that is the third orbit, it will have 3 subshells and so on. Now, what will be the range of these subshells? Or the numbering of the subshells. The subshells will be numbered from 0 to n minus 1. Okay. So, if n is equal to 1, then let's consider N, L and the number of subshells. Okay. So if N is equal to 1, then the number of subshell will be 1. So what will be the value of the azimuthal quantum number here? That is 0 to N minus 1. So we put 0. Now what is N minus 1 here? N is 1. So 1 minus 1 will be 0. So 0 is already there. So first orbit will have only one azimuthal quantum number, that is 0. Now if N is equal to 2, then there will be two subshells. One will be 0 and another one will be 2 minus 1, that is 1. So two subshells are matched. For 3 we will have 0, that is 0 to N minus 1. That is until we reach N minus 1, we will add 1 at every step. So the first one is 0. So we will add 1 to 0. So we get 1 and then we will add 1 again, we get 2. Then if we add 1 again, we will get 3. But the limit is N minus 1 and N minus 1 is 2. So this is the maximum azimuthal number that is applicable for N equal to 3. So there is 3 subshells. Add 1 at every step until we reach N minus 1. Okay. Similarly, for N equal to 4, we will have 0, 1, 2, 3. Now 3 is 4 minus 1, that is N minus 1. So this is the maximum. We will not go any further. So we have 4 subshells. So these are matching. Okay. Now for 5 again we will have 0, 1, 2, 3, 4. So there will be total of 5 subshells and so on. Now these numbers have some different names according to the shape of the electron cloud. So what are the name? L and name of the subshell. For L equal to 0, the subshell is denoted with S. For L equal to 1, the subshell is denoted by P, small p and small s as well. For L equal to 2, the subshell is denoted by D. L equal to 3, the subshell is F. L equal to 4, the subshell is G. L equal to 5, the subshell is H. But we don't require much up to G and H. The most required subshells are S, P, D and F. Among them, S is spherical, P is dumbbell shaped, D is double dumbbell and F has some complex structure. We will discuss about the shapes of the subshells later on. So, if we write together, what we will have? N, L subshells. Okay. For N equal to 1, L is only 0 and 0 means S. So, the subshell will be called 1S. For N equal to 2, there will be two subshells 0 and 1. So we will call them 2s for 0 and for 1 2p. For n equal to 3, we will have 3 azimuthal quantum numbers 0, 1 and 2. 0 is s, that is 3s. For 1 we will have 3p and for 2 we will have 3d. For 4 we will have 0, 1, 2, 3. Now we have 4s, 4p, 4d and 4f. So these are the principal quantum numbers, azimuthal quantum numbers and the name of the subshells. Now we had seen that azimuthal quantum number is also known as angular quantum number or angular momentum quantum number, because this helps us to find out the angular momentum. Orbital angular momentum. Can be found out by L. So if it is denoted by capital L. So capital L is given by square root of L into L plus 1 into h by 2 pi, where L is the azimuthal quantum number. Okay. So for S subshell, what will be the angular momentum? Root over L into L plus 1, right? For S, L equal to 0. Therefore 0 into 0 plus 1 into h by 2 pi. So this comes as 0. For P subshell, we have L equal to 1. So capital L will be 1 into 1 plus 1 into h by 2 pi. So this will come as root 2 into h by 2 pi. For D subshell, L is equal to 2. So capital L will be 2 into 2 plus 1 into h by 2 pi. So we get 2 into 3, that is root 6 into h by 2 pi. Similarly, for F subshell, L is equal to 3. So we get angular momentum as 3 into 3 plus 1 h by 2 pi. So this is root 12 into h by 2 pi. So we had said the shapes of electron cloud. So S orbital is spherical like this. P orbital is dumbbell shaped like this. D orbital is double dumbbell like this. Okay. We will discuss about the shapes of the electron clouds in further details. But now we will discuss about the quantum numbers first. So, we have discussed n is equal to the orbit or shells. L or azimuthal quantum number is subshells. Now, it was found out that when we were discussing about the limitations of Bohr's model, we had said that Bohr's model was unable to explain Zeeman effect and Stark effect. What was Zeeman effect? Zeeman effect was that the splitting of the atomic line spectra into finer structures in presence of a magnetic field. And Stark effect was splitting of the line spectra into finer structures in presence of an electric field. Bohr's theory could not explain these splittings. But now, when the splittings were found out after knowing about the quantum mechanical model, then it was found out that these splittings can be explained by the third quantum number, that is called the magnetic quantum number. So, the third quantum number is the magnetic quantum number m. Okay. Why magnetic? Because it explained the splitting of line spectra in presence of magnetic field, that is Zeeman effect. This explained Zeeman effect and Stark effect. So, it was proposed by Alfred Landé, and this is denoted by the letter m, and m denotes the orbitals. So, we have principal quantum number n, which gives the orbit or shells, azimuthal quantum number L, which give the subshells, and now we have magnetic quantum number m, which gives the orbitals. So, now we came to the conclusion of Schrodinger wave equation, which gave us three numbers n, L and m. We have discussed about the principal quantum number and azimuthal quantum number. Now we will discuss about magnetic quantum number and the fourth quantum number which came later. Thank you.